Hey everyone again, and welcome to this video tutorial on Linux system calls. This will actually answer quite a few of your questions on how system calls can be used in the assignment and beyond. So let me start by just reminding you of what system calls are. And these are basically a set of interfaces by which the process can go from user space to interacting with the kernel or kernel functionality. And it is used for controlling the hardware, for example, creating new processes and communication between different processes that exist. Maybe on not, I mean, they might not be even sharing the same parent or anything, but they might just need some communication and some other services from the operating system, for example, reading from disk, writing from disk, getting more memory, releasing some memory, and these things. So, uh, syscalls are an abstraction, and they basically provide this abstraction to the user and the applications. The applications do not really care what kind of hard disk you're running on, or what is the type of memory module that you're using. I mean, what make is it? Doesn't really care about what mouse you're looking at, or what screen you're using, or what even, I mean, even to some extent, what graphics card for a normal graphics application you're using, for example. So they provide an abstraction for applications on the types of on the hardware that is being used. They should also ensure system security and stability, so you should not do things that would introduce any sort of insecurity or some instabilities, some undefined behavior in the system. So they provide also security and stability. It allows the kernel to arbitrate between different processes because it using system calls you can actually check if these if two processes are competing for the same resource, which one has, for example, the right permissions, which users have higher priority, and so on. So you can actually use them to do these kinds of arbitration. And together with exceptions and traps, upcalls, they are the only legal way to go from user space to the kernel space. So you cannot, as a user level application, go into the kernel except through using syscalls. And syscalls are actually architecture dependent. Well, they are not architecture dependent. It's wrong to say that, but some syscalls are supported on some architectures, but are not supported on others. And by architectures, we are talking about the CPU architecture, for example, and maybe even some of the media types. I mean, if you have a GPU on your graphics card and these things, you can have syscalls that are only supported by your by an architecture. So if we talk about the x86, your computer processor, versus the ARM64, which is the processor on Raspberry Pi, there is a difference between the different system calls. And for Linux, there are about 335 syscalls for the x86 architecture, which is basically a normal computer architecture. And basically, that's for x86 only. So you might have a subset of that or a superset of that for other architectures. And there's a very interesting thing that not all operating systems that exist actually publish their exact syscalls. They have some abstractions over the system calls, making them even much worse in performance. The system calls are in general, I mean, since you need to do the context switching from the user to the kernel space, they are typically slower to invoke than a normal method. Although things that are implemented as kernel in kernel space might be faster because, well, they have higher priority, they do not need to ask for permissions and so on and so forth. But the context switch itself, I mean, if you have a method that can be implemented in user space and the same method can be implemented in kernel space, and when you implementing it in user space, you do not need to have any further syscalls than the one in calling user space method or calling a user space function might actually make more sense because it's faster. And as I said, not all operating systems publish their exact system calls, and some operating systems are estimated to have over 1,000. Actually, Windows 8, and this is published, has 1078 system calls according to their online guide. So, I mean, Windows had that habit of actually not revealing what system calls they have, and people would actually try to hack Windows to understand what system calls are there because they might be useful for many programmers. Okay, so uh, as an average programmer, you do not typically use system calls. You do not go and call a system call directly into the kernel, but you use an application programming interface to call a system call. And that's what most people are familiar with. It might be that the API, the call for the API, actually overlaps with the name of the system call, but for example, fork. But that doesn't mean that you're just calling the system call right away. You call an API basically, and if you look at this figure, this sums up how system calls are actually how it works actually in real in programming. You typically have a print f a sys.out.println in Java. I mean some print function, so printf in C, print in Python, sys.out.println or sys.out.print in Java, and you call and you call basically the function in the library, in the language library from the application. The language library calls a function that is like, for example, printf in the C library calls a write function in the C library. And this is basically the POSIX abstraction that we're going to talk about in a little while. And then this one is the one that calls the write system call in reality. And you can see that, well, you're changing from the application level I mean, it depends on what kind of application you're running, um, uh, what kind of programming language you're actually using to implement the application. Because, for example, in Java, you even have the JVM lying somewhere in between and so on. But in general, you basically have these transitions between the application till the language internally inside the language library and then the system call. So let us look at the POSIX interface basically. And POSIX is a standard that was designed by the IEEE, one of the leading technical organizations in the world that basically manages almost everything related to engineering in many ways, especially I mean, both professionally and academically. So this is where, for example, academics publish conferences, publishing conferences that are run and organized by the IEEE. So there are a series of standards from the IEEE that basically define how a, li- a library, a programming library, should interact with the operating system. And you typically see that the POSIX defined API have a very strong, or APIs have a very strong correlation with what the system calls that are actually implemented in Linux are. And it's almost universally implemented for almost every single programming language you can think of. So you can see it for Python, for Java, for C, and basically they implement the standard. So the standard is implemented. Actually, a language like Go, for example, implements the standard by just implementing this by just calling the system calls. So there are different design decisions that are related to using POSIX actually. Okay, and Linux system calls are accessed via function calls to the C library. That's the way you would do it in normal programs, and they are defined in the C library. I mean, you can actually go to this link, for example, C POSIX library, to look at that, and you can have arguments going into the syscall, and your system call can result in one or more side effects. And these side effects can be, for example, to allocate memory to some process, to open a file. I mean, these are sort of side effects. Writing to a file also, these are also such side effects. But there are some syscalls that do not have any side effects. For example, the getPID syscall that basically returns to you the process ID. It has no side effects, as in it does not change things on the system, it just gives you back a value. The return from any system call is always long. I mean, all system calls will have long as the return value. This is a rule of thumb. Okay? And getting a positive number usually signifies success. A negative return value would usually denote an error, but not always. I mean, it's a mess like everything in operating systems, basically. Do know that the Linux operating system has been maintained for over 20 years now, and things have changed, basically. And a lot of this is even inherited from Unix, which means that a lot of this is just, well, legacy. So usually, though not always, a negative return value would denote an error. 0 is usually a sign of success, but again, not always. Okay? So if you get an error, then you get an error. There is a variable that's called error no, so which is error number basically, and this is basically used by many functions to return error values. So if you get an error in your system call, that the error will be an error no, an error number, and you can actually use a function to translate that error, and that's, for example, p error. There's a function that is called p error, to which you pass the error that you get from system call, and then it will just tell you that, okay, this error corresponds to you have no access to this file, for example, or this file does not exist. Okay. Okay, so let's look at an example of system call definition. Syscall define 0 is a macro. Syscall define is the macro that defines how system calls are implemented. And if and the number over here, the number at the end signifies how many parameters are going to be passed to this system call. How many parameters does this syscall return? Okay. So getPID, for example, is defined here as a system call that gets as input 0 inputs and returns the current tasks. The current tasks thread TGID, which is basically the thread group ID. And we haven't really talked about the thread group ID, but if you have just processes, normal processes, the tgid is equal to the normal PID. So if you have just processes, then this is, well, if you're not doing multi-processing or multi-threading, then your tgid is basically your application ID, your PID. With threads, it gets a bit different because you get, this is the thread group ID, which basically signifies that these threads fall within the same group, i.e. they share the same parent, for example, okay? Or they share the same grandparent. You set it based on thread groups, okay? This enables basically a thread to call getPID and get the same PID. So all of the threads will call, if all of the threads in the thread group calls the getPID, they would get their thread group ID, knowing that, okay, this is sort of our group. Okay, you can get the per thread PID also. That is also implemented, but this is what getPID does. Okay. So now that we have looked at the macro to define if one of the syscalls, you actually also need to expand the code definition in another file that we're going to talk about later as follows. So you have to basically define your syscall using ASM linkage, which is the modifier, and then long, which is your return type. And then if this is the name of your syscall, so if, for example, in your project, the name of your syscall is basically get data, then you would define it as sys underscore get data and any input that you would like to add, which might be the user ID in our case, for example, in the project, in the assignment case, sorry. ASM linkage is basically a modifier on the function definition, and it is a directive to tell the compiler to look only on the stack for this function's arguments. So it tells the function that tells the compiler how this function will actually get its arguments. One way to actually make your assignment easy would be if you just implement it such that it returns the current user. I will accept these as valid results for the assignment. But if you're able to basically add on stuff, then you, as we agreed, you get more credits by doing more stuff. Anyway, the get PID system call is defined as sys get PID in the kernel, and well, this is the convention for naming it. You also have syscall numbers because, well, each system call will get an assigned number, and the way that the application or the user level call will be to the system call will be using that number. So this number needs to be unique, and it needs to be unique throughout the kernel. So you cannot have two syscalls with two similar IDs. And that also means that for backwards compatibility, if you had a system call that you have removed from your kernel, I mean, we're talking about hardcore kernel development here. If you have removed one of your system calls, you cannot reuse the syscall number, because then it might be that some other application is, well, I mean, the programmer didn't know, or they is using an old library basically, and that basically results in it using the old syscall number that you just removed. And then if you reuse it to do something else, then you might end up with complete havoc in your system, and your system be extremely unstable. So processes do not refer to the syscall by name, but rather by the number. And you keep the number per syscall in what is called the system call table. And the syscall table on x86-64 architecture is this table, and if you look through the internet, Linux 2.6, the older versions, you'll find in the tutorials, for example, adding syscalls, a different architecture for syscall tables. Basically, the x86 syscall table was not in this file, but was somewhere else. But let's not talk about it. We're now at kernel 4.x. I can't remember 4. What now today. And then for ARM64, and actually for most architectures, you have a generic table for syscalls that basically stores the syscall name and the syscall number, and the kernel can basically, from that, the kernel can basically say, okay, I got a 4, and 4 is the right syscall. I should do something right, basically. And that's the place to basically look at it. Okay, it's ASM generic / unistd.h, but also, I mean, you find it sometimes. You sometimes find redundant information in the kernel, because, well, some different parts compile differently. But I mean, this is basically where you find the syscall tables, these two. And this one, the second one, is actually your entry point to implementing the assignment, to add new system calls basically to the system call tables. So this is the syscall table for ARM64, and it looks something like this. you have basically, so these are the syscalls. So sysio get events, for example, and it has the number 4, and this sysio submit, and it has a number 2, and sysio cancel, and it has a number 3, and you can see that this is how the syscall numbers are defined in the unistd.h file. Okay. And I also thought that it might, since we have been talking about the get PID a lot, so this is basically the definition for the syscall number for get PID, and it's 172, and this is a standard. So I mean, when you redefine it, when you define your get data, that's cool. I mean, you call it whatever, but that's the say that in your assignment you're going to use the name get data, then you would basically need to define the new number as last underscore underscore nr underscore get data and put a number, and this number has to be unique, and then you basically need to find what is unique and where is unique. And it's actually pretty well documented. You see, and one thing to note, I mean, if you're adding a new system call, you should basically add it towards the end. You should never come and say that, oh, I am going to add it here and shift everything that comes below by 1, because that will basically completely screw up your kernel. So you add your new system call, you define the number towards the end, and that number should not be taken, should not be here. Okay, so this is the syscall table for ARM64, and this is the one for basically x86. Okay, so and you get basically the number. I mean, this is the definition: number, ABI, name, and entry point. And we are not going to really talk about the ABI now, but ABI is, well, is it something that is 64-bit specific or 32-bit specific? We have not talked about the register sizes, but we'll talk about that a bit later. And basically the system call name and the syscall definition, basically. Okay, but when you define a system call, you also need to define sys and to add it to sysni syscall, which is basically a place to put all those calls that no longer exist. So if you are as a kernel developer, go on the Linux kernel list and decide with Linus Travel and the other guys that, oh, we do not want this system call anymore, we should remove it. So for backwards compatibility, you should actually add this as to this file as something that has already been deleted, no longer exists. But also, you need to add your new call here too. And the reason is it provides failure mechanisms so that you can fall back to this. So if you suppose that you did not get your implementation right for the system call, you don't want your whole system to break because, well, the system call does not exist, break, right? So you basically define it also here. And basically, I mean, the way things would work is that it will try to find it first in the syscall table. If it does not, then it will just jump here. Okay, so these are two things to, or this is one thing to note when defining system calls. So now let us talk about where do you add your next kick-ass, super duper, very cool syscall. And there are multiple places, multiple files where you can add a new syscall, and you should pick them based on well, what the syscall is going to do. But one of these places is kernel/sys.c, and there you find definitions of multiple system calls that are related to the system. And you also find some of them commented in a language that probably most of you understand. But that's basically where you get most of the system related definitions. And you can see, for example, the get PID and system related definitions is not that it starts with the sys underscore name, system call name, but things that are related to the kernel system. So if you are, for example, on the there is a reboot system call that is defined in reboot.c because that's where it makes sense to implement it. I mean, by defined here, I mean implemented. There are things that are related to the file system that will be basically written or implemented in the file system. But this is one of these implementations, and you see that the definition over here is basically quite short. So system call defines 0 get PID, and then it returns the current thread group ID. But also you have a get TID, which is get thread ID, which basically returns the internal thread ID for the kernel, okay, for the kernel thread, right? And you get implementations that look like that, for example. So school defines 0 get PPID, and then here it does a little bit more than just returning something from the kernel. So in your case, it's probably a good idea to, you might want to, no, I wouldn't say it's a good idea. You can actually add it to a separate file, or you can add it to sys.c towards the end, your new system call for the assignment. Let's talk about how the kernel actually uses the syscalls or manages the syscalls. So the kernel basically uses what is called a syscall handler, and a syscall handler is basically an interrupt handler. It's an exception handler for the system call. User space, the way that user space applications basically tell the kernel that they are in need of a system call is that they trigger an exception by, I mean, this is the way it works in reality. And the exception switches to kernel mode, switches that from user mode to kernel mode, because it's an exception. It's sort of an interrupt basically, and then as we talked about in the second lecture, there are exception handlers, and the syscall manager or the kernel basically treats this as a software interrupt and basically starts running the system call the exception handler, which we talked about in the second lecture. This is pretty architecture dependent, because the exceptions, the exception handler, as we said, for these interrupts are mostly hardware defined and hardware implemented. I'm not going to go into this little detail, but there are basically places, I mean, where you need to implement this in actually assembly to get the correct system call number. And then you have a function that is called system call void that takes anything, that doesn't take anything as a parameter. And you do not need to worry about it, but this is basically how the mechanism works. Again, let's continue with how the mechanism is. You check basically the validity of I mean, once you have that, you're done with the architecture specific stuff. Is that a system call, or is that, I mean, is that exception due to some hardware interrupt, or is that exception due to the user space trying to call a system call? Now you know that you're in the system call, then the system call function basically compares the system call number to the table to basically check if that system call that you're trying to call exists. If it doesn't exist, basically due to the numbers, you cannot find the number in the system call table, then you basically say that it does not exist and call the ni syscall file. Otherwise, you basically start the system call that you have just found in your system call table. And then there are details on how the memory is referenced for that. So each element in the system call table is 64 bits, and that basically means that the kernel multiplies the given system call number by 4 to arrive to the right location in the system call table, and this is just for x86. This is very x86 specific. Okay, and the actual implementation has actually nothing to do with the mechanism. So what the past two slides were basically how the flow goes from the user space to kernel space, and including how it deals with the hardware interrupts. Okay, uh, or the software interrupts using the hardware. But the actual implementation has nothing to do with the mechanisms. There are a few rules of thumb when you start implementing a new system call. First one is that you try to never multiplex system calls. So you should not have a get PID one process, which basically, well, a system define get PID and then have one, where you basically say that this system call, if it gets as input number one, then it will return the thread ID. If it gets an input number two, then it will return the process ID. If it gets three, then it returns the parent's ID. I mean, this is very frowned upon. Uh, you should not have the input to the system call controlling the output of the system call. If it's worth it, then just implement a new system call. Okay, if it's something that people will feel towards, then we implement it newly. So it could have been that, for example, in the get PID system call, we saw that there's a get PID and there's get TID system calls that sort of one of them returns the process name and the process number, the process, the thread group ID, and the other returns the thread ID. You could have implemented them in one and basically multiplexed on the parameter, but that is bad. Okay, think about it as you need clean and simple interfaces, because this is something that people will use and need to understand. So if you make it, the more complex you're going to make it, the much worse that experience of programmers will be when using it, of system level programmers. Okay, and you want it with the smallest number of arguments possible. Actually, there is a limit on the number of arguments, and if you go beyond that, then you will need to actually reference memory in the stack to basically say that, okay, these are the more arguments. And I think the limit for x86 is like 6 arguments. It's either 5 or 6 arguments, and if you have more than that, then you just go and start reading memory and start understanding arguments yourself. So keep your arguments as minimal as possible. You should think that an interface, a syscall interface, will not be something that is used today, but something that will actually live with Linux for the next 10 years. So that's for general syscalls. That's not for your assignment, though. Your assignment is something that will die after the course, maybe live on your GitHub accounts. So design it to be as general as possible. So if you can design your syscall to be usable for different architectures, that's super. If it's not architecture dependent, or if there is a way to make it not architecture dependent, such that it does not hurt performance a lot, then it's a good thing to do. You should not also make or you should try to reduce assumptions on the architecture's word size, basically how many bits is your processor, and its NDNS. And well, you probably forgot about what NDNS is, but you can look it up at Wikipedia. It's one of these things that people keep forgetting about. But the reason for that is that, well, you have an ARM architecture that was basically 32-bit, and now there is a 64-bit architecture out of ARM, and you can actually, from processor to processor, from basically family to family in the same processor architecture, so ARM 64, change NDNS. And well, this is not nice, but it is actually true. And there is a very interesting Linux philosophy that you need to keep in mind, is that you are providing mechanisms, not policy. You provide ways, but you do not tell people how to do things. So now to the sweet stuff. You need to verify the parameters, right? So if you have the input data, the get data syscall from your assignment, and basically I input to it my name, it should not work. It should it should do what it is supposed to do. It should take either a user ID or a username. Okay, you can take a username, but if my name is not my username, Let's put it that way. I mean, there are open things that were left for you specifically for your design, basically. But let's say that it takes user ID as a number, and then I input it with my name. It should fail. It should not basically break things, and it should just fail and tell you, oh, you shouldn't use that. So system call runs in kernel space, and you need to make sure that user parameters are, sorry, the submitted parameters are correct. And Linux provides you with some mechanisms to actually help you with this process. One of them is that if you want to write to user space from kernel space, you use copy to user function. That is defined actually over here. And that is basic. Oops, sorry. So that is defined over here, for example. And for reading from user space, it provides you also with another function, which is copy from user. Okay, so if you're reading from user space, this is what you use, and if you're writing to user space, this is what you use. And there are checks on this function. Of course, you should make extra checks if you need to, but getting input and providing output to user space, you should think about these two methods. And both of them would return the number of bytes they failed to copy on error. Okay, so how many bytes did that call fail? On success, they return 0. So let's look at this. Can you tell me what does silly copy do? If you just, so this is a system call definition that is called silly copy. Takes as input, has basically 3 inputs. Okay, so system call define 3 and does something. Can you basically tell me what it does? Okay, there is also a check so that because not all users are equal, so there is what we call a capable what is called capable function. And capable is to check if the caller is allowed to perform an action. We have not talked about users that much, but users can have different capabilities. There are normal users, like people on the normal, I mean, that have not been given higher privileges, and there are root users. And root users are basically super users that can interact with the kernel being less careful than it would be with a normal user. So capable is the function that you would use to basically check if the user is allowed to do this change. And for example, you basically have capable and between parentheses caps is nice. So can this user basically, or does this user have a capability to change the nice values of other processes? And Linux defines a lot of these capabilities that users can do, and then you can basically, I mean, the default case is that super users have all capabilities and non-root users have no capabilities. Okay, so this is the default value, and basically the capability flags that I'm talking about, I mean, they are all in this file. So let's look at, for example, the reboot syscall that I was talking about. And this is basically a call to that does reboot. And you do not want any user to basically go into your terminal, into your computer and type reboot. So a guest user, for example, when you fire up Linux, you can get a guest user. You don't want that guest user to just go in and type reboot and then, ooh, he just rebooted my machine and I just lost 1 month of work that I forgot to save. So you check for this. Does that user have the power to reboot? And the philosophy is that we only trust the super user with rebooting the system, and then you basically check if the user is capable of doing capsys boot, basically. Okay, and that's basically you can find these checks all over the Linux kernel. So now we are almost done with everything that is actually related to syscalls. Um, But then the question is, how do we implement our assignment? I posted with the assignment a link, which is basically this link that points you to a document that says about adding syscalls. It actually tells you about the formal process to add a syscall for Linux, but it also tells you how to do it, as in implementation wise. Go there, go to this file, change this, and so on and so forth. So if you follow that, you will be able to basically have a system call running, and it should be. I mean, I I think that almost all the details are in there, with also I mean, for building and stuff, you can find more details on the Stack Overflow question. I actually encourage you a lot to, if you face a problem, to go to Stack Overflow. Not that, I mean, Stack Overflow is one of the most useful tools for you as a programmer and as a developer, and it's not just for the operating system. It's actually it's for everything. So you should get accustomed to it. And for your programming jobs in the future, you actually find in the programming applications, in the applications to submit an application for a job, they actually ask you for your Stack Overflow handler. So that they can basically see what kind of questions you have been asking, but also what kind of answers you have been giving to the wide public. So I encourage you to use Stack Overflow. Actually, I mean, I would mind if you get your whole code from Stack Overflow, but I wouldn't mind you asking specific questions on Stack Overflow and even pointing me to them in your reports. I would actually appreciate that, because that's kind of nice, right? It gives you training on the job. Also, the book that I talked about, which is basically the Linux kernel development book that I actually got you in the first lecture. There is a chapter 5, I believe, which talks about system calls. The only problem with this book is that it actually covers an older Linux kernel version. So if you are going to follow the guidelines of this book, then this is actually, some of this is obsolete stuff. I have no problem with you doing that, but then you basically will need to find or download the version that the Linux kernel development book is talking about, and follow the guides there. But still, I mean, it's not a long read anyway, and it's available in the university library now. Okay, so again, it's chapter 5, so you should be able to read it in here also. So follow the guide. Then, if the final thing is basically how to show that it works. Suppose you just added a full syscall to your system, and placing a macro on top of your C program is all that it takes to get your stuff running and showing it to us that it works, basically. So you have defined a new full syscall that has the number 283, and you basically use this macro to basically point the C compiler to where it should where it will find the system call, and then you implement your C program as usual. So you have the stack size equals full, and then, well, it's a function to basically find the stack size, and then you print the stack size. Okay, with this I conclude. Thank you very much, and talk to you very soon. Oh, one more thing. Okay, I forgot about that. If you want more about the syscalls in ARM, if you're really into ARM architecture, then these are actually good sources for this. Okay, thank you very much, and yeah, see you all very soon.